So one of the big to-do items in 6004 are the labs. The way you get to they're basically weekly labs, except weeks when we have quizzes, in which case we have no assignments due. The way you get to the labs is you go to the course website and you click on the online assignments link. And that will, if you give you a little table showing you what you've submitted and what you haven't. And in the left column of the table, there are things labeled L1, L2, L3. There's buttons you click. And when you do that, the lab page opens up in your browser. You do everything through your browser. There's nothing to download. All the design tools actually, God help us, are written in JavaScript and run actually pretty well on your browsers. We seem to have had good luck with the latest Internet Explorer and Safari and Chrome and Firefox. If you have any difficulties, we'd be glad to help you sort them out. The corollary of that is probably good to give it a try, so that if you have difficulties that need sorting out, we can do that somewhat before, 2 hours before the lab is due. So labs are due on Thursday. The first lab is actually not due. It's actually due 2 weeks from today. So you have a little bit of time to get started, but after that it's a very regular rhythm. And I always encourage you to get started in the labs. Give them, at least open them and look at them and make sure you understand the scope of the work, so you leave plenty of runway to get them done. You can, the staff can pull up your designs, so that we can basically see exactly what you see on your browser page. Remotely. We will pull the same information off the server that you do. And so what that means is that if you have a question on your circuit, when you post on Piazza, if you post so that we know who you are, so you feel free to post so that you're anonymous to your friends. If you have sort of a generic question like it doesn't work, that's fine. Otherwise, do a private post. If you have a long description of your circuit or something, we're very happy to deal with you and help you remotely. It's just that we don't really want to publish your entire design to the rest of the class. So anyway, give it a whirl. We'll be glad to try to give you a hand remotely or in the lab. We're starting the staffing of the lab on next Monday. So, and away we go. Any questions about the lab stuff? I'd try clicking really soon now just to make sure you're at least, sort of know how to get to the destination. Then you can choose. Yes? Yes. If you all did that, then we'd have an easy semester. So, actually, I should say the courses, the exams are unfortunately scheduled. So, those we'll still have to do. Some people get way ahead. Some of the labs they don't expect you to do. We try to schedule the lab so the material you need is done the week before the lab is due. But it is the case that if you start trying to design your beta now, you might say, God, I don't know how to start. And you might, so to be fair, we haven't really talked about half the things you need to know. So we will in plenty of time. It's just that we haven't yet. Other issues, questions? Okay, so today what we're going to do is to explore the digital world. We're going to figure out why everything that we use these days in terms of electronic equipment to manipulate any sort of information. Well, we're going to figure out why we make it digital and how we make it digital. It's actually sort of fun because we could have done anything. We've actually, over the course of many decades, evolved a fairly sophisticated strategy. It's a very nuanced strategy in the sense that it's designed to address a lot of problems. So today we're going to talk about the problems that it addresses and how it addresses them. And after today, you'll be able to know what it means to be digital. So we've talked about, we're going to use bits to encode our information. And what we're interested in doing is to figuring out what representation we're going to use for bits, because that representation will of course determine the machinery we use to do computation and storage and communication. We would like our bits to be cheap and small because we want a lot of them. So for example, carrying around the Rosetta Stone would not be, it has the advantage of being quite stable. You know, it's an artifact that's lasted for thousands and thousands of years. But it's not terribly handy if you want to add it. If the Pharaoh woke up one morning and decided he had a new decree to add to the bottom of the list, you know, it'd take somebody 2 hours with a chisel to add it. Obviously, we want our information to be much more malleable. I should say, by the way, that we would like our information to be as long-lived as the Rosetta Stone is, and that's a puzzle we're still working on. Conceptually, our information is very long-lived. Practically, if you're like me, your bits rot. You know, that picture you took 3 years ago Tuesday, you know, where is it now? And so, you know, either you've carefully stored it away, you're good at doing that, and you put it someplace safe that in theory should last forever. And we'll just hope no one kicks out the plug on the Google server farm, and we lose our bits. So how we choose to represent information is determined a lot by what goals we want to achieve. So cheap and small. We want them stable. If we put in a 1 today, we'd like to come back and still have it be a 1 tomorrow. And of course, we're interested in building machinery that might, for example, manipulate bits, you know, at many billions, make many billions of changes a second to, you know, this vast array of data. And so that suggests things like stone tablets aren't a good idea. At the other end of the spectrum from stone tablets, if you want small, I'll give you a small. Here's a molecule, right? DNA. DNA has actually been very good at storing information for millions of years. It sometimes gets modified, sometimes for better, sometimes for worse. But the chemistry of life turns out to be a very powerful compute mechanism. It's very good at doing certain operations. And there's actually a fair amount of research here at MIT about how to use the chemistry of life and these sorts of molecules to do interesting large-scale computations, you know, in a bucket of goo. This strikes me as fascinating stuff. It may be that we'll all have, you know, little bits of organic computing all around us in the years to come. However, we're in electrical engineering and computer science, not biological engineering. So we're going to use things that, you know, electrical phenomenon, which have some advantages. So we could use voltages or currents. And in fact, most of the devices we have use a sort of a mixture of both. For example, most of the information that's stored in your machine, it's stored in several ways. It's stored electrically. It's stored as a voltage in your DRAMs. It's stored as an orientation of a magnetic domain on your hard disk. It's when we read out information from flash, we're often measuring currents to determine whether it's a 1 or a 0 or something like that. We could also use phase and frequency. We often encode information using phases and frequencies, for instance, for wireless communication. So from here to the access point, there's a lot of orthogonal frequency domain multiplexing signaling that's going on between my laptop, or I should say your laptop, and the I've learned to turn off wireless. It's amazing what will pop up on your screen in the middle of a lecture. So there's many different choices. It depends on our application. We're going to use voltages. So voltages are easy to us for generate. We have a lot of engineering expertise in voltages. There's a plug on the wall that promises delivers, you know, both voltages and current to us. It potentially offers a chance to have our systems operate not only at low power, but almost zero power. And we can, if we're clever about how we design our logic circuitry that uses a voltage-based representation, we can make it so that if nothing is changing in the circuitry, it's basically not dissipating any power. And that's the miracle that allows us to all put our phones in our pockets and carry them around all day, and you know, with a fairly modest battery, and still have them do pretty neat things for us. There are some downsides to voltages. One is that they're fairly easily affected by the environment. There's lots of sources of electrical noise, and we'll talk about some of those in 2/3 of the way through the lecture. And so we'll see that noise looms large as a problem that we're going to have to deal with. You know, maybe we could pretend it didn't exist and struggle through. No, we're going to actually have to face the fact that the world is full of noise, and the goal of being digital is to have an engineering technique that lets us build circuits that work perfectly even with noise. Okay. So, how do we represent information using a voltage? Here's a picture. Something looks familiar. To represent the information of this picture, we might use a scheme where a voltage between 0 and 1 volts, and 0 volts would represent sort of a black element of a picture, and 1 volt would represent the brightest, the white elements of the picture, and everything in between is represented by some fraction of a volt. So if it's 37% gray, so forth and so on. So just thinking about an individual pixel for a moment, we'll talk about how to encode the whole picture in a second. Individual picture, how much information potentially can we store at each point? Well, it has to do with how reliably we can distinguish voltages. So for example, if I can reliably distinguish voltages that are close to 0 and close to 1, but we're a little confused in between, we could represent one bit of information, so a 0 and a 1, and we could just use, one of 2 voltages, because I can only really distinguish 2 voltages in my circuit. If I can distinguish 1,000 voltages, or let's say 1024 voltages, then I can represent. So I'm capable of determining to a thousandth of a volt or a 10/24th of a volt what a voltage between 0 and 1 is. Then I could have 10 bits of information, 1 over 2 to the 10th. Because I can uniquely distinguish a voltage as corresponding to one of 1024 different values. What do you think your plausible value for n is? Yes? 16. So you're feeling pretty comfortable that you could reliably distinguish a 65,000th of a volt. A 16-bit DAC, right? Okay. So so now the questions are we should ask ourselves is how quickly can we do that? Can we every billionth of a second make a new measurement? And most 16-bit DACs don't quite work that fast. And so there's a bit of a trade-off between resolution and speed. So that's a good thing. The other thing as we'll see is that certainly most of the noise that we would encounter in our circuits that are just live here in the room are quite a bit smaller than the 65,000th of a volt that we have, that we're measuring to. So our measurements actually are probably much more precise than the voltage, the accuracy of the voltage we're trying to measure. So what n should be is actually an interesting question. We're going to pick n equal to 1. We're going to basically store one bit of information, encode one bit of information in a voltage, using voltages. We'll come to that. So how do we represent a picture? Well, we basically just create an analog waveform by taking the intensity, the luminosity of the picture as we scan across and use that to generate a voltage between 0 and 1. We then make many such scans across the picture, and we end up with a waveform that looks like this. This is the old black and white TV waveform. There are special little markers in the voltage waveform that indicate when I get to the end of one line and get to the start of another. Everybody sort of got that? So that's an analog way of representing this picture. So let's build a system now. So we're going to introduce two operators. One's copy, and so its job is to basically produce on its output terminal the same voltage that's on the input terminal. And invert basically produces 1 minus that. So white turns to black, black turns to white, so forth and so on. So this, you can see this is the negative of that picture. And the first question is, why are we using components? Well, components really are our key to building very large systems. We need to be able to take a stack of components that offer particular pieces of functionality and sort of wire them together to get the behavior that we want. So back there in the control room where there's a lot of video circuitry, it's not like somebody sat down with individual transistors and wired everything together. We bought a video switcher and a video amplifier and an audio this and an audio that. These were big building blocks that are connected together. So connecting things together by building blocks is something we want to do. So this is not a bogus experiment from an engineering point of view. We would like it so that once I have components, I should be able to build as big a system as I want to just simply by plugging all the components together. Big system, small system. We expect this to be able to compose the components reliably. Okay, and this is important because there's a lot of us who are not destined to be EEs. right? So we need things that, I don't know how it works inside, but if I connect the cable here and the cable there, it's you know, I have a video system. So I'm a 6'3" pretty much, except I occasionally do, I alternate. I love software, then I say, oh, hardware is a lot of fun. I think the puzzle of building good hardware is great. And then I go build hardware and I remember how much reality sucks, you know. And I say, you remember that nice virtual world of software where everything sort of works? And so I alternate back and forth. So, alrighty, so the idea behind our system strategy is that the components work and we follow the rules for how to hook them together, we would expect our system to work. And that's going to be important when we want to build large systems. So let's build a system. Well, just a whole chain of copies and inversions here. What do you expect out? Well, there's an even number of copies, which should not change the picture, and an even number of inversions. So I expect to get the same picture out. So that's what theory tells us we should get out. In reality, it's a little fuzzy. So it's actually interesting to think about why it would be a little fuzzy. What is there about our system that caused something less than perfect to come out of that thing? And so it's actually that thought experiment and figuring out what went wrong, okay, that will tell us a lot about how to build reliable computing systems. So this was a picture processing system, and it seems to be slightly less than perfect. Alrighty, so the copy operator doesn't work right. What would that mean? If I say the copy operator doesn't work right, maybe what I'm suggesting is that if you have a copy operator, like so, and I put in the voltage V, what I'm getting out is V plus or minus a little bit. What's the little bit? Might just be a thousandth volt. It might be something small. Where does this little epsilon come from? Well, it comes from either manufacturing variations, some resistor is off by a little bit here. It could be power supply or temperature that's causing the system to not work quite right. Okay, it could be actual electrical noise that's causing that voltage to wiggle a little bit. And you say, well, it's just a little error. But now we get to the and we have the same problem with the inversion operator. Now we get to the real crux of the matter. Why was a little error? Why we say it's just a little error? Why does that really matter? Why does it seem to produce a detectable difference at the end, particularly as our system gets larger and larger and larger? Yes? It adds up. Basically, the errors accumulate because the system has no way of knowing that V plus a little bit is a signal with some error in it. It just thinks of that as the legitimate signal. So the next stage takes that as a perfectly legit output. It adds a little error to that. So the errors accumulate. So in a lot of analog systems, the more components you put together, the more the errors accumulate, and the sadder the outcome. So the plan, one of the issues then is that our theory about how this is working is imperfect. That if I had carefully put this, told you this was the model, the correct mathematical model for the copy operator, you would have said, okay, now I can probably predict exactly how much the picture will be different. Okay, so, but it's sort of sad to mess up something that was actually a very easy system to explain, and now it's full of Gaussian noise distributions, and what do you expect at the end? And you're saying, oh my God, I have to go do real math to figure out what will come out. So our theory wasn't good enough, but we don't really want to produce a theory that would completely accurately present, because that would make the system very hard to use. Reality is imperfect. Yes. Reality, of course, to be fair, it probably says, well, I got here first. So what I do is what I do. Your job as engineers is to build things that work even when Mother Nature is just, Mother Nature being Mother Nature, right? So reality is imperfect, and that's what we're going to have to do. So the bottom line, the answer here, of course, is all of these things are wrong, is that we didn't choose a very good system architecture, because as we tried to put things together, our system performance degraded more and more and more. So that would be awkward. It would be awkward to have an internet that if I went from here to the back of the room was fine, and if I went from here to West Campus, you know, it didn't work so well, and by the time I got from here to China, you know, bits were completely gone. That you would not feel that was a successful system architecture for transmitting information. We need to design our system to deal with some amount of error. Error happens, some amount of noise. Noise and error, I think of those as the same thing. We need to be able to tolerate that. Okay, this is why we're going to go digital. What we're going to do is, instead of thinking of an analog voltage on a wire, and what we're going to do is to think of bits on the wire. In fact, we're going to put one bit on the wire. And we're going to take our analog world of time and voltages and things like that and create an abstraction, an abstract digital world that basically only has zeros and ones in it. So the next part of the lecture really is figuring out how to interpret voltages digitally. Right, so the idea is that even though there's small changes and bad things happening in the real world, we'll still have a very reliable, you know, representation for zeros and ones. So that's our mission. Okay, so attempt number one, suppose I just pick a threshold voltage. I have a range of voltages I can represent. And I put a threshold voltage in the middle, and I basically say, look, anything less than that threshold voltage is a zero. And anything greater than that, and like, look, I've even mathematically, I've taken care of the, you know, the boundary condition and everything. Okay, everything greater than or equal to that threshold voltage is a 1. So how is that as a definition? Well, obviously, since on your slide you see an attempt 2, there must be something wrong with attempt 1. What's wrong with attempt 1? Why are we feeling a little, you know, why should we be gun shy about this? I mean, mathematically, it seems to make a lot of sense. Yeah?
What happens if we're like exactly at 0.5?
Well, if we were exactly at 0.5 volts, the formula tells us we're a 1. The thing is that, although you sort of touched on the issue, which is right around that threshold, we have a very tough measurement to make. Right, if I'm really going to build a machine that completely accurately implements this specification, it's very hard to tell the difference between 4.999999999 and 5.00001. And you're going, no, it's not, Chris. There's a 4 in the first one and a 5 in the second one. It doesn't seem hard at all. No, but if you had to build a device to do the measurement, you can see that device, particularly around the threshold, it would start to be very expensive and start taking longer and longer and longer to make us decisions. So even though we like the idea of a threshold marking, you know, the boundary between zeros and ones, what we're going to do is to make a small modification to this and have 2 thresholds. We're going to have a low logic threshold, V sub L, so V sub low. So voltages less than V sub L are treated as a 0. Voltages greater than the high threshold, V sub H, are treated as a 1. And voltages in the middle we're not going to treat as anything. We don't interpret them. We're not allowed to ask what those voltages mean. They don't have a digital, a voltage in this range does not have a meaning as a bit. Right? Only voltages less than VIL or greater than VH, greater than or equal to VH. How does this help? Why is this definition somehow solve the problem that I was struggling with a bit there? Yeah.
You can still lose meaning, but you don't get like the wrong thing anymore? Or less wrong?
So give me an example of something that is now less wrong that was more wrong before.
Well, like, so if we're at the very edge and we go over, now instead of being the complete opposite of what we wanted to say, it's just like, it's not what we wanted to say, but it's not what we wanted to say either.
Right. Okay, so you're still saying there's still some boundaries and boundaries cause issues. I'm going to talk in a second about that's not, it turns out we can solve that problem. In fact, we can solve it very simply. But yes?
How do you store that third state binary?
Well, see, this is not a state. This is just, we're just talking about, well, we know how to store 0 and 1. I mean, zeros and ones are the 2 bits. We're just saying that if I run across a voltage in my circuit in the immediate thing, in the intermediate range, in the forbidden zone, that we can't say whether it's a 0 or 1. So what I'm going to do is I'm going to build actually a fairly crude device it does have a single threshold. So, suppose I built myself a little op amp. Voltage comes in here. There's a voltage divider here that helps me detect, this is a particular threshold voltage here. And so, but these resistors are cheap resistors, so exactly what VTH is, I don't know, but it is somewhere in this range. It's somewhere in the forbidden range. Okay, but it could be here, it could be there, it depends what device I buy, it doesn't really matter. The point is, would that device still allow me to just obey the rules? It would reliably, assuming the threshold was guaranteed to be in some small region here, it would still reliably report a 0 for things that were less than V sub L, and it would reliably report a 1 for things that were greater than V sub H. Okay, and it would be reporting things in the middle, but we're not allowed to check it in that sort. We're only allowed to check it when the voltages are less than V sub L or greater than V sub H. So what we've done is we've left ourselves some elbow room. Okay, and we'll see that we need one more little change to this specification in order to get good digital signaling, and we're going to run across that in a slide or two. But everybody get the basic idea? We've left ourselves a lot of manufacturing elbow room to build a device that converts voltages either into bits. Okay, and they can have a threshold anywhere in here, it doesn't matter exactly where, so long they get the answer right when the input is less than V sub L and when the input is greater than V sub H. And otherwise they're allowed to answer whatever they want. So that's going to be sort of our key to being able to make these devices manufacturable. So, we'll come back to the small change in the signaling spec, but let's say we have a digital signaling spec, and for now it's those two logic thresholds. I'm going to give you the rules for building a device. And what we're going to do, the rules will make a lot of sense to you. I mean, they'll say, okay, that's a good description. We'll discover there's some interesting implications of these rules. Okay, so that'll come right at the end of the lecture. So keep your eyes open for those coming large. So a device is a combinational device. So combinational is an adjective that has a specific engineering meaning. I'm going to tell you what that is. And when we actually build logic circuits, we're building them out of combinational devices. Devices that satisfy these 4 criteria. 4. Okay, they have digital inputs. Now what does it mean to be a digital input? It means that the device will take any voltage on this wire, on this input wire here, that's less than V sub L, and it will treat it like a 0. And it will take any voltage that's greater than or equal to V sub H and treat it like a 1, and we're not allowed to ask what it does with voltages in the middle. So that's what a digital input, a combinational device is engineered to interpret one range of input voltages as a 0 and the other range of input voltages as a 1. It has digital outputs. What's that mean? Well, that means it produces voltages, following the signaling spec. So if this device, digital combinational device, is supposed to produce a 0, it produces an output that's less than V sub L, and once it produces 1, it produces an output greater than V sub H. Everybody got the plan now? So if I told you what V sub L and V sub H are, and I start listing voltages, you would be able to very quickly tell me whether it was a 0, corresponded to a 0, or corresponded to a 1, or you could say, you can't ask me, it's in the forbidden zone. So combinational devices have digital inputs and digital outputs. They include a functional specification that tells you for each possible combination of inputs, okay, what the output will be. In this case, how many possible combinations of digital inputs are there? There's three wires, 3 digital inputs. How many different things, if I were going to give you a description, I have to take care of how many cases? 8, because each wire can have one of 2 values, 0 or 1, right? And so I can go from 0, 0, 0 to 0, 0, 1 and all the other possible combinations. And for each of those combinations, I would tell you what the output would be. And then I would have completely determined the digital behavior of the device. I could build a table that basically enumerated for each digital combination of digital inputs what the output value was. We call that a truth table. We'll meet that in the next lecture. Okay. And finally, there's a timing specification, which at a minimum tells you how long you have to wait before, once the inputs are valid and stable, how long you have to wait for an answer to come out. 1 nanosecond, whatever it is. Okay, so these 4 things are what we call the static discipline. So a combinational device is a device that obeys the static discipline. Okay, so these are mostly sort of definitional right at the moment, but we're going to start using them to get some more information about what sort of circuitry we can build that will satisfy the static discipline, that will actually be a legal combinational device. Okay, but first of all, let's go back to system building. So my claim is that if I have a whole stack of combinational components, each one of which meets the static discipline, I can plug them together in any size circuit that I want, and the resulting, if I follow the following rules. Okay, every circuit element is a combinational circuit element. Every input is connected to, so I'm looking now at the inputs to each element, is either connected to exactly one output from some other combinational device, or is connected to an input to the circuit. This is basically the same thing as saying I can't take 2 outputs and short them together and connect them to an input. In other words, there's no shorting together of outputs. There's never anything, well, this guy's saying 1 and this guy is saying 0, and you put the wires together and now I don't know what the right answer is. That's disallowed by our construction rules. So no short circuiting outputs together. And the circuit contains no cycles. In other words, I can basically, if I trace every path from input to the output, I never visit the same device twice. No cycles. Okay. I claim that if you follow these rules, that the overall system that I've just built is itself combinational. In other words, I've got a composition rule that's hierarchical. I can take little combinational devices and make medium ones, and I can take medium combinational devices and make big ones. I can compose arbitrarily large combinational systems. Why is that true? Okay, well, let's answer that question. A, B, and C are combinational devices, no cycles. I can follow all the paths and see there's no cycles. No outputs are shorted together. So, what are the 4 questions we have to ask and answer about whether this is a combinational device? Does this overall device, the one sort of inside the blue box, does it have digital inputs? Yes. Thank you. Oh, I love it. Okay, so convince me it has digital inputs. Give me a sentence that says it has digital inputs because? Right, the property of these inputs is sort of inherited from the places they connect. Right, so since A had digital inputs, these 2 devices, these 2 inputs to the system obviously are digital, and the same thing for B. So the whole system is inheriting some properties from its components. What about does it have digital outputs? Yes, for the same reason. Can you complete a functional diagram? If I gave you the functional specification for A, B, and C, could you tell me the functional specification for the blue box? How would you do it? What is it you need to do? Yeah, go ahead. Right, basically I have to make a table that for each possible combination on these inputs, I have to tell you what the output was. And what you're saying is, so fine, I'll put 0, 0, 0 here, and then I need to figure out what the output of C is. Well, how do I do that? Well, I can use the A table to figure out the value of that wire, then I can use the B table to figure out the value of this wire, and then I can use the C table to figure out the value of that wire. Right, and the reason that we don't want any cycles, that if one of these wires looped back, it would be, you couldn't really reliably compute the output value because it would be a function of itself, and it would be unclear what the answer was. So with no cycles, though, I can always systematically go through the circuit from inputs to outputs and find out the values for all the intermediate wires and sort of propagate the information about the inputs and their reprocessed values all the way to the outputs. How about a timing specification? Can you derive sort of how long you have to wait to get the answer out? And again, with no cycles, the answer is sure. I have to wait at least, no, A tells me it will have its answer by a certain time, by time 1. B tells me it will have its answer 2 time units, say, after its inputs are valid. So now I'm at time 3 and C has its inputs. And now starting at time 3, I can calculate how long C will take, because I have C's specification, to compute its answer. So I can very systematically use the properties of the components to deduce the properties of the system. So the whole thing is combinational. So this is the sort of the secret to success. Notice that I'm not giving you little weasel words about errors accumulating or anything. Everything is nice and clean, and I can build arbitrarily large combinational systems and expect them to work. That's the key. I can expect them to work. Will this system work? We're going back. We're going to go fix our signaling spec, our one little bug in the signaling spec. We have a combinational device that's producing a voltage that's just under V sub L. So it's outputting a 0, but just barely. You know, it's so close to V sub L that if any noise happens, the signal is larger than V sub L when it gets down to the input of this device, and this device no longer says, I don't know if it's a 0 or not, it's bigger than V sub L. So here, even though we've got everything working great inside of these devices, once we start wiring them together, we have to worry about issues introduced by the interconnect. So how are we going to solve that problem? How are we going to make it so that even if I produce a valid output voltage, that some things can happen to it, and I still end up with valid input voltages at the far end? Yeah? Yeah, we're going to actually have sort of different thresholds for outputs and inputs, and it's the difference in those thresholds that will allow noise to happen. That's exactly what we're going to do. Okay. So where does this noise that I'm worried about come from? And first of all, you might be thinking of cosmic rays and thunderbolts and noise, not noise. Okay. The answer, unfortunately, is most of the noise that we're worried about comes from just the operation of the circuit itself. If you're switching on and off currents in the circuit, okay, if you have little digital switches in here that are opening and closing to perform logic functions, and you're routing voltages and currents around the thing, that itself will produce noise. It will produce small variations in voltages, either due because you're taking current and you're running it through a wire. Now, the wires have very low resistance, but they don't have zero resistance. So there is some there's some very small voltage drop across every conductor. Okay, it could be that that when you change the amount of current that's being drawn, as you suddenly start doing a heavy computation and a lot more current is coming through the pins of your chip, those pins have inductance, and when you change the current through an inductor, you get a back EMF, and so you get this LDIDT drop. This is all we're going to do with electricity, by the way. So if the word LDIDT drop is like, whoa, I didn't do so well in 802, thanks. The idea, we're not going to do the actual arithmetic. The idea is that you should be aware that as you change voltages and currents across components, you get these sort of effects that can affect the voltage. Okay. We can certainly imagine that resistors that are nominally 10 ohms, it could be 11 ohms, they could be 9 ohms, and they introduce the design voltage here will be a little different than the actual voltage because of variation of component values. And then finally we do get to the noise that's introduced either by thermal noise or by external E&M fields. So we do have things. These are not so hard to solve, at least the E&M fields. We can put everything inside a little copper box of a little Faraday cage to insulate ourselves from external electric fields. These are I build an electric circuit. There's going to be, these effects occur all the time. So I have to be prepared to deal with them. So here's our plan for modifying the voltage spec because of all those items of noise I just talked about. Okay, I'm going to have 4 voltage specifications. I'm going to have VOL and VOH, which represent the voltage thresholds for outputs. So when I'm producing a signal, on the output signal, a digital output, we'll have to produce a signal less than or equal to VOL to produce a 0, and a signal greater than or equal to VOH, okay, to produce a 1. So it's really the same thing as before. I've just relabeled the output threshold here. But I'm going to introduce a separate threshold called the input threshold, okay, that determines how to interpret voltages when you're an input. So you can see that I've arranged things, in fact this is important that I've arranged them this way, along the number line this way. So in fact I'm accepting a bigger range of input voltages as a legal zero than I asked of the outputs to produce. And the difference between a legal output low voltage and a legal input low voltage, okay, that's called the noise margin. Because this represents how much noise can be added to an output signal and still be treated as a legal input signal when it gets to the far end. Okay, now wouldn't it be cool if we could find digital devices that basically had very low VOL and a very high VOH, and then we had VIL and VIH sort of close together in the middle, and we said to ourselves, that would give us a huge noise margin. And wouldn't that be great? We get lots of noise. And in fact, the things you carry around have great noise margins. Okay, and next time we'll meet CMOS circuitry. CMOS circuitry turns out to be wonderful in many ways, but one of the most important ones, it has very large noise margins, which means that it can operate in a variety of circumstances and still get the right answer. Used to be in the old days, computers sat in very special rooms that had temperature control and very carefully engineered power supplies and lots of cooling to keep it just, you know, exactly the right temperature and everything. They were very sensitive to environmental changes. Nowadays, you know, we carry our devices anywhere and we're sort of pissed off when they don't work and I'm standing in the North Pole. I wanted a selfie at the North Pole. What do you mean you're not working? So we have very high expectations and we're able to meet them because, in part because we've done a really good job of recognizing how environmental effects affect our system and then engineering around that. So back to this. Everybody understand about noise margins? The idea that by having separate output and input specs, we're allowing things, bad things to happen to good outputs and still have them be legal inputs. Okay, so you'll see this is a good thing for you to sort of focus on because this is the key to digital signaling, is this notion of these four thresholds. When you buy a logic device, okay, they come, the specification sheet you give comes and it will tell you those four specs. I mean, it will tell you, if I'm outputting a zero, I'll output a voltage in this range. If you're sending me a zero, you have to send it in this range, and you can actually look and see that all the devices have noise margins. Okay, so let's think about what does this tell us about a device? I have a very simple device here. This is the actual schematic symbol for a buffer. A buffer is like the copy element. So it's a digital copy element. If you put in a zero, you get out a zero. If you put in a one, you get out a one. You might say, well, why would I want a buffer? You'll especially as you get to the end of the course and you're trying to make your fancy beta circuitry run faster, you'll see that buffers can be your friends for reasons that you'll learn about. Okay, but let's think about this device. What I'm going to do is to populate, I'm going to run the following experiment. I'm going to produce what's called the voltage transfer curve. The voltage transfer curve is basically a bunch of measurements. I'm going to put a bunch of different input voltages here that range from 0, say in our case, to 1 volt, the legal signaling range. And for each input voltage, I'm going to wait a little while until the output is steady, and I'm going to measure the output voltage. And I'm going to plot the V in versus V out curve for the device. Everybody got the idea of the experiment I'm running? V in versus V out curve. I put in an input voltage, I wait a while, and I measure the output voltage. On both of the V in and V out axes, I put the thresholds just to give us something to look at. One of the things, and this is now we're getting to the interesting part, I claim that no combinational device will have a point that falls in that shaded region. Why do I think that if I measure a device and I measure its voltage transfer curve, why am I insisting that if there's a point, one of the measurements I make has a point that falls into that region, I'm going to throw the device away and accuse it of not being combinational? Yeah?
Because a combinational device can have for output
Yes, but that's a good start. We're getting there. Yeah. Right. So remember that if I give, so this is really pretty much what you said. The idea is that if I give an input in this range, any voltage that's less than or equal to VIL, what is the device required to produce after its propagation delay? If it's a valid digital input, a combinational device must produce a valid digital output. So a valid digital output is a voltage less than VOL or greater than VOH. It better not output anything that's between those two voltages, because otherwise it wouldn't be behaving. Everybody good with that? Everybody sort of appreciate why those shaded zones are there? Right? They represent regions that are valid inputs but invalid outputs. Okay, so if I went off and measured such a device, I would expect to see something like that. A curve that looks like that. Okay, in a moment I'll explain, I don't really care what it does in the middle. I care about its behavior when the input is less than VIL, and you can see the output is producing a legal 0. When its input is greater than or equal to VIH, you can see it's outputting a legal 1, a voltage above VOH. Everybody good with that? So this is a buffer. You can say it doesn't produce the same low output voltage, but so long as any voltage that it produces that's less than VOL will be a legal output voltage. Okay, so you look at this curve. This curve actually has a couple interesting features, the most important of which we're going to get to here on the next slide. So here's the VTC. It goes like this, and notice that it's not going through any part of the forbidden zones there. Our devices don't have to behave themselves, okay, in the middle. Okay, for input voltages between VIL and VIH, they can do anything they want. They can produce a high, they can produce a low, they can change their mind, they don't have to be valid, they can oscillate, they can do whatever they want. Now, mostly we'll design them and they'll behave pretty well. They'll have a sort of a smooth, continuous behavior, but that's not required by the combinational device contract. Okay, but the other thing I want to point out, let's go back to this picture here. The other thing I want to point out is, what can you tell me about the relative size, the width of, so see this region right in here between the two forbidden zones? What can you tell me about the width relative to the height of that region? So here's the region, and it has a width and it has a height. And so here's the forbidden zones over here and over here. What can you tell me about the relationship between W and H? W will be less than H, right? The region is narrower than it is high, and that was because we had positive noise margins. VIL is larger than VOL by some amount, and the same thing is true of VIH and VOH. Now, why do I suddenly look at that? Because now I know something about the types of circuitry that I need to build. Because in this region here, our combinational device has to have gain. Now, gain is really just a measure how much is the instantaneous gain at a particular input voltage is basically the slope of the line. How much a small change in V in, how much V out change you get. So the gain is sort of like the amplification. I make a little change in V in and I get a big change in V out. I'm getting a lot of gain out of the device. So our combination logic has to have gain. Okay, now that means that passive components won't do. I cannot build combinational logic out of resistors and capacitors and inductors, right? They are not devices with gain. They're linear devices. They don't have gain. They don't suddenly produce a much bigger voltage out. Okay. The other thing that I'll say about this curve is that given that there's a gain greater than 1 here, if I think about the shape of the diagram, that means the device has to be nonlinear. In other words, I can't draw a straight line from one side to the other and build a combinational device out of that. The gain has to change. The device can't have a gain big enough to get through this region that's narrower than it is high, okay, and still get through this region without getting in the forbidden zone if the gain doesn't change. It has to have low gain here and high gain in the middle. So we need to build combinational devices, okay, that have gain greater than 1 and are nonlinear. And we need to look for electronic devices that we can use to build our circuitry that have those properties. And as I say, resistors and capacitors and inductors don't got it. So with teeing up that for next time, we'll suddenly come across some devices next Tuesday that will, miracle of miracles, allow us to build combinational devices. See you in recitation tomorrow.